Hi, and thanks for joining me today on CuriousBen.com. If you guys are tuning in from YouTube, you want to head over to the website CuriousBen.com, where you'll find a little brief introduction to what we're working with today. It's how to solve compass error by amplitude. I got a little disclaimer about how we're going to teach you how to do it there today, and I've got a full copy of the exam question that we will be solving. So let's jump right into setting everything up. Like we talked about before, I like to set all of my information up the same way every time. Okay, so I always write down the date and time first, then the lat and long, then I'll get the chronometer reading, the error, I'll solve for the time, get the zone description from the longitude, apply the zone description, get GMT. That's how I start every one of these. Okay, I recommend however you want to write it all down. Just make sure, like I said before, that you're consistent and you always keep the same kind of like layout on the page, because it's going to make it a lot easier when you're going through it. It makes it, that repetition, that muscle memory is going to make it easier to remember and kind of just make your life a little smoother as you're solving these. It makes it harder to forget the steps that you're taking. So I went ahead and I kind of created a layout like you see in the other page. And we're going to go ahead and type in all the information from our exam question here. Now, the exam question, this is one of the actual U.S. Coast Guard exam questions for the upper level licenses. This is exam question number 01651, if you guys want to look that up on your own. Or, like I said, it's on the website. Okay, so date and time. They do not give us a time for our local time, but they do give us the date, which is the here, let's actually tell you what, let's go back. We will put all of the new stuff in red so it's a little easier to see. Okay, date and time. So the 23rd of October. And we're going to have to do a little bit of working to figure out whether this is morning or evening, but I'll show you how to do that in just a second. Okay, 1981, getting ahead of myself. Okay, latitude in this is 21 degrees, 13.0 minutes north. Longitude, 152 degrees, 18.0 east. Okay, so we're going to need this as a decimal when we're entering our arguments in the Nautical Almanac for latitude. And we're going to need the longitude as a decimal so that we can figure out what our zone descriptor is. So we'll go ahead and figure that out right now. I already know what this is going to be, so it's going to be 152.3. And the way that we do that is we take that 18 and then we divide those minutes by 60, right? Because we're trying to find whatever the decimal of the minutes is, right? 60 minutes is 1 degree. So we take that 18.0 minutes divided by 60, tells us the decimal representation of our longitude is 152.3. Okay? We're going to do the same thing for the latitude. The latitude is going to be, I should have written that down somewhere, right? Didn't I? I didn't. Okay, we'll just punch it into the old calculator here and figure it out. 13 divided by 60 equals 0.21. That's easy. All right. 21.216. Okay. So that 152.3, our decimal for the longitude. Next thing we're going to do is we're going to have to solve for the zone description. So when we go to what time it is, we're going to need to figure out Greenwich Mean Time, because that's how we're going to enter all of our arguments into the Nautical Almanac to find out what our amplitude is supposed to be. And they give us our chronometer reading and the error. We don't know whether it's AM or PM, because remember, chronometer time is just like a watch, right? Your chronometer has only got, 12 hours in it. So your timepiece, that is your chronometer, it doesn't tell you whether it's AM or PM, but I'll just go ahead and skip forward to it. we already know that we're dealing with 259 degrees PSC, right? So 259 degrees, what does that tell us? That tells us that we're looking to the west. So since we're looking to the west, we know that we're dealing with the sunset. We know that we're dealing with a PM problem. So basically, we're going to have to add 12 hours to our 0700 hour time. Okay, so when we get our chronometer time, we're going to add 12 because we're dealing with a sunset, which happens in the evening. Just chronometer time is only 12 hours. They don't have 24-hour clocks, I suppose, when you're doing your Coast Guard exam. Okay, so zone description. You take 152.3, divide that by 15. That gives us our zone description. Our zone description happens to be 10. Now, this is just like true virgins make dull companions to correct the compass. We at W, at weddings, add west, add west. This is east, so this is a negative 10. Okay, plug our negative 10 in there. Okay, chronometer reading from the question is 07, 21 minutes, 46 seconds. Okay. 21:46. Chronometer error, 1 minute, 32 seconds. Okay, 1 minute, 32 seconds. We do the math, and that works out to be 19:23:18. Why is it 19? Because we have to add that 12 because we're looking at a sunset. It's in the PM. We know that there's no way the sun is setting at 0700 in the morning. Okay, right? So chronometer time here is 19:23:18 because we had to add this because our chronometer is slow. Okay. Apply the zone description to the local time. That'll give us Greenwich Mean Time. Minus 10, Greenwich Mean Time is 9:09:23:18. So even though it's sunset, it's nighttime where we are, back in jolly old London, it is 0900 in the morning. So this is how we're going to enter the Nautical Almanac, is using Greenwich Mean Time. Okay. Now what we'll do, we'll go ahead and bring up this copy of the Nautical Almanac page. Okay, we're going to look at 1981, October 23rd. Okay, 23rd. And we want to make sure that we're in the sun column. Okay, they have a couple different pages for each day. You got to make sure that you're looking at the right thing. We're looking at amplitude of the sun. Okay, 23rd, Greenwich Mean Time, 0900, right here. Okay, this is what we're interested in, the declination. GHA stands for Greenwich Hour Angle. We will need that for different types of problems, but not this. Declination, south, 11 degrees, 0900, that's 25.6. Okay, now we can go back, write down our declination, south, 11 degrees, 25.6. Now here's an important one. Go down to the very bottom here. Look at the very bottom. Okay, you see this D? We need that. Okay, that is going to be what we look up in the very back to get what the actual declination is. Our D, right there, 0.9. Okay. Now, this could be a plus or a minus. I guess we'll just go back to this here real quick and look. Okay, 11, 25.6. Next one's 26.4. Next one's 27.3. They're going up, so this is going to be a positive correction. That's going to be a plus 0.9D. Okay. So when we actually look up what our correction is, we're going to add that to get our correct declination. Now, I'm going to go ahead and skip looking it up in the back, but nautical almanac, there's the white pages in the beginning, the yellow pages at the end. The white page tells you what it is for each hour. The yellow page corrects for the minute. So we look in the yellow pages for 23 minutes, and we don't care about the seconds because for amplitude, all we need is to correct the D. So we take this 0.9, we look that up on the sun column of the yellow page. We don't care about the 18 seconds, just the D value. That 0.9 D gives us a D correction, all of that, bump, 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 plus 4. Okay. Just skip looking that up just for time's sake. So now we know that our declination is south 11 degrees, 25.6. We're going to add 0.4. So our corrected declination is south 11 degrees, 26. Okay. Once again, we're going to have to divide by 60 and get this as a decimal. Okay. And that's going to be 11.43. So now what we're going to do is we're going to take the sine of 11.3, divide that by the cosine, sorry, I didn't write that down there, the cosine of the latitude as a decimal, which is 21.216. Okay, and then we're going to get the sine to the -1 of this whole thing. Okay. All of this is going to equal out to be 12.27. Okay. Now horizon, question mark. Okay. Let's just get some fresh paper here and kind of look at this. They mentioned that the center of the sun is on the visible horizon. So when we look at the visible horizon, it's a curve, right? The actual plane of the celestial horizon, which is a flat line, if we were to go ahead and stick a plane through the entire globe, the celestial horizon would be a flat line. So there's a difference between when we see half of the sun on the visible horizon and when we see the sun halfway on the celestial horizon, right? Actually, I think is that correct? I can't recall if the celestial horizon is above or below the visible horizon. But regardless, all you need to know is that when you're correcting this, you got to go to the green bow ditch if it's on the visible horizon and look up the correction for visible horizon, okay? Because all of the amplitude is actually figured off of the celestial horizon. So now that we've answered the question, yes, we do have to correct for it. We're going to go to the green bow ditch. Once again, I'll save you looking that up. It's table, not 27, I forget which one it is. You can look it up in the index, but correct amplitude for visible horizon. And it's going to give you a correction. And the correction for our declination and latitude, which are the arguments that you use again, is plus 0.3. So the correct answer, our amplitude, is 12.57. Okay. Now, once again, we have to solve for whether or not we're east or west, which we already know. It's 270 degrees. Okay. Our correction was 0.3. It's always going to be a positive for these amplitude problems. We're always going to add that correction, okay, because it's going away from what they call the elevated pole, okay, so 12.57. Now, is this above or below 270? Okay, this is below 270, so we're going to now subtract the amplitude, and that's going to give us our true value. So 270 minus 12.57 is going to give us what it actually should be. Our true vector should be, when we're looking at the sun, 257.6 6.5. Okay, variation 5 degrees east, 5 degrees east, gives us a magnetic heading. The sun should appear to be 252.5, but it's actually 259 degrees. So what is the difference here? What is our deviation? This is the answer. This is what we're solving for. Well, 6.5 degrees, add wedding, okay, add west, so 6.5 degrees west. Okay, there you have it. 6.5 degrees west is our deviation. Well, if we look at what the Coast Guard answers are, we've got A, which is 0.9 east. We've got B, which is 1.5 degrees west. We've got C, which is 5.9 degrees west. And we've got D, 6.5 degrees east. Well, which one's the closest? 6.5. The Coast Guard does this, okay? They don't give you a correct answer, but they do try and trick you by giving you a wrong answer that looks like it. Closest one to 6.5 degrees west is going to be 5.9. Now, like I said, this is a little different than how you actually do it, okay? Sine of the declination divided by the cosine of the latitude is a simplified version of it. Technically, it should be sine of the declination minus sine of the latitude times sine of the elevation. Elevation for the difference between celestial horizon and visible horizon, I believe is 0.7, negative 0.7. That would be the altitude. Okay. So it's technically sine of the declination times sine of the latitude minus or times sine of negative 0.7 divided by cosine of the latitude times cosine of the altitude, which is once again cosine of negative 0.7. You work that whole thing out. The answer that you're going to come up with is 12.55209. This is the actual true and correct amplitude. You can see that we got here 12.57, 12.55. This is so close. If you just do sine of the declination divided by cosine of the latitude, you'll always get the right answer. Okay? There's a lot of problems like this where they don't have an actual correct answer. You got to just pick the one that's the closest. So 5.9 west, answer C. That's it. There you go. You can see how it differs from what the actual amplitude is. You can also look it up in table 27 of the green Bowditch. And then you got to kind of interpolate between 4 different numbers usually, because there's no actual, declination of, 11.43. It'll be declination 11 and a half. And then the latitude will be, 21, 21, 22. So you got to interpolate. It's just messy. It's not very accurate. So the best way to do it, to get the answer, just trust me, sine of the declination divided by the cosine of the latitude, get sine to the negative first power, that whole thing, and that'll get you the answer. So in this case, there you go, 5.9 C, and that's how you solve for amplitude. All right, guys, well, I hope that kind of helped you out. I know it's not an easy one, but we'll make another video here to kind of explain exactly how to solve for the actual amplitude, but this is how I do it. You'll always get the right answer for the exam. Just remember, it's not going to be exact. Pick the closest. Thanks for tuning in. Have a great day.